Here we have an object on an inclined plane, and if we look at all the forces that are acting on it, we have the force of gravity that's acting straight down. We have the normal force that's perpendicular to the plane. We have the force of friction that's parallel to the plane. It makes sense in this example to use axes that are parallel to the plane and perpendicular to the plane. The reason it makes sense is that our motion is parallel to the plane. And so that's going to be what we want to look at. We don't want to look at acceleration that's in some component that's horizontal, because that's not going to be helpful to us at all. So we want to break this vector, our gravity vector, up into components that are parallel and perpendicular to the plane. The way to do this, and if you just follow these steps every time, you'll end up with the correct angles, and you won't have to think about it too much because it's always going to work out the same, is you draw your vector going down the plane. That's going to be the component down the plane, and you draw far enough until, if you draw the vector going down to the end of that angle, this angle right here would be a right angle. Now this angle here, we'll just call it theta. So if you play around with the geometry, you'll find out that this angle right here is also theta. So if you just look at it, look at your parallel lines and perpendicular lines, you can convince yourself that that is true. And since that is true, then and this side is mg, then this component, the component perpendicular to the plane, will be mg cosine theta, and the component parallel to the plane will be mg sine theta. So if you use that general method to break up your vectors into components, you'll end up that with the force of gravity, if you break it up into components, the part that's perpendicular to the plane is mg cosine theta, the part that's parallel to the plane is mg sine theta. And what that usually means, not always, but it usually means your normal force is also mg cosine theta, because usually you don't have any other force perpendicular to the plane. Now that would change if you had like a rope on this, or if someone were pulling up on it, but usually this force and this force have to be equal to each other. Okay, so let's look at an example where we're going to use some actual numbers here. And I think we have a skier. Now, I don't know what mountain this skier is on. I don't know if it's the one on the front of the book or not. It might be. Okay, so we have the skier has just begun descending the 30-degree slope. Assuming the coefficient of friction is 0.10, calculate her acceleration and the speed she will reach after the number of seconds. It said 4 seconds. Okay, so there we go. That's our setup. So let's draw our free body diagram. Okay, first I'll draw my inclined plane. I always draw my inclined plane first. My angle is almost never the correct angle, just from the way it looks. But
that looks fairly accurate.
Yeah, okay, not too bad. Okay, so now I'll put my skier up here. I have a point skier. That's my skier. What forces are acting on my skier?
Gravity.
Got gravity down.
Societal pressures.
What's that?
Societal pressures.
Yeah, societal pressures, yeah, there's some forces. What else?
It's in friction.
Well, yeah, so it gives us a coefficient of friction, and so we know the friction will be opposite the direction of the motion. She's going down the slope, so it'll be in that direction.
Normal force.
We have a normal force. And then what do we always want to do?
Break into components.
Yeah, we want to break things into components. It's not showing up down here. There we go. Ooh, that's a yucky color. There we go. Okay, so to draw our components, I'm going to draw my vector down the plane. Now, if I had forces going up the plane, I'd draw my vector going up the plane if I were like pulling this up, but instead I'm going down. So I'll draw my vector in this direction until I get to the point that if I draw a vector to the end of this arrow, I'd make a right angle. This angle will now be 30 degrees if I drew my components correctly. The side perpendicular to the plane will be mg cosine 30. The side parallel to the plane will be mg sine 30. Is this going to equal our normal force?
I would hope so.
Yeah, because we don't have any acceleration perpendicular to the plane. So we know our normal force equals mg cosine 30. Now, at this point, you may be a little bit panicked because you look and it's like, wait a minute, I don't have the mass of the sphere. Oh dear, what's going to happen? Well, if that happens, you just hope that things will cancel out. So we'll see if they cancel out. Okay, what's our force of friction?
It is move this kinetic and then interwise.
Yeah, so it's our kinetic friction, coefficient of kinetic friction, which is 0.10, times our normal force, which is mg cosine 30. I'm just going to be dealing with the component that is parallel to the slope, so I don't have to worry about breaking it up into components parallel and perpendicular to the slope. So what are my net forces, and what do you want to call positive and what do you want to call negative? It doesn't matter.
It's called going down the slope positive.
Down the slope positive, everyone okay with that? Okay, so we have 0.1 times mg cosine 30, and then minus,
Negative component.
that is going to be the negative component because that's the friction, because we decided that we were going to call down positive. So down is positive, so the component that's down is mg sine 30. The component that's up is the friction, which is minus 0.10 mg cosine 30. That's F net. F net is going to equal mass times acceleration. So mass times acceleration equals mg sine 30 minus 0.1 mg cosine 30, and yay, we were hoping our masses would cancel, and look, they do. Alright, so our acceleration equals 9.8 sine 30 minus 0.1 times 9.8 cosine 30, and has anyone done that?
Yes, 4.05 meters per second down the slope.
4.05 meters per second squared down the slope. So that would be her acceleration. So they have it in terms of g. Okay, so now let's find the speed she will reach after 4 seconds. How do we do that?
Multiply by 4.
Yeah, because we know that final velocity equals initial velocity plus acceleration times time. So our final velocity will equal 0 plus our acceleration, 4.05, times our time. So our final velocity equals 16 meters per second.